Hi, I'm Shashank, and I'm going to present our work MoRAG, Multi-Fusion Retrieval Augmented Generation for Human Motion. Our code and pre-trained models are available on our project webpage. Text-driven human motion generation has seen significant progress, with diffusion models excelling at generating high-quality motion sequences for familiar text descriptions. However, they struggle with complex or unseen inputs, highlighting the need for strategies like retrieval augmented methods to enhance the adaptability and performance. Retrieval augmented generation involves enhancing generative models by incorporating external knowledge retrieved from relevant data sources. This technique improves the accuracy, contextual relevance, and reliability of the generated outputs. Existing text-to-motion retrieval approaches focus on retrieving full-body motion sequences from motion databases. However, these strategies struggle with text phrases containing spelling error, synonym substitution, or rephrased text sequences, leading to reduced performance. Additionally, these existing strategies struggle to retrieve motion sequences for text descriptions that are not part of the dataset, limiting their generalization capability and diversity. As a result, there is no effective motion retrieval method that can be seamlessly incorporated into the motion generation process to ensure scalability, diversity, and enhanced performance across a wide range of text inputs. Our goal is to develop an enhanced motion retrieval strategy that efficiently serves as an additional knowledge engine for motion diffusion models, improving their performance and adaptability across the language space. So, we propose MoRAG, a retrieval augmented framework assisted by large language models, capable of generating high quality, improved, and semantically coherent motion sequences. The lower row showcases the retrieved motion sequences for corresponding complex text descriptions, with colors representing part level retrieval. The upper row showcases the generated motion sequences conditioned using MoRAG's retrieved sequences. MoRAG is an augmented retrieval method that integrates part-specific motion retrieval models with large language models to enhance the performance of retrieval tasks across diverse text descriptions. MoRAG Diffuse is a diffusion-based model that incorporates the MoRAG retrieval framework, further improving motion generation. The idea behind the part-wise setup stems from the observation that existing datasets contain extensive low-level body part information. This information has the potential to generalize across a significantly broader language space. As we adopt a part-based motion retrieval approach, we prompt the input text description to an LLM to generate motion descriptions specific to the torso, hands, and legs. Our prompt consists of three components. First, we have the task instructions, which summarize the task details. Next, we provide a set of example descriptions to ensure the model understands the format of the output we are expecting. Finally, the query consists the input text description. The input text description is prompted to the LLM, which generates part-specific text descriptions corresponding to the torso, hands, and legs. The part-specific text descriptions are then used as queries to retrieve the corresponding part-specific motions from the respective part-specific motion databases. The retrieved part-specific motions are then composed based on the joint information to construct full-body motion sequences. Our objective is to construct three independent part-specific motion databases. To achieve this, we train three motion retrieval models: MoRAG torso, MoRAG hands, and MoRAG legs, each designed for a specific body part. These models are trained independently using part-specific body movement descriptions generated by large language models for text phrases, along with their corresponding full-body motion sequences. Each motion retrieval model includes a part-specific text encoder, and motion decoder, although we simplify the process by omitting motion decoder here. A contrast to training objective is adopted between the part-specific text embeddings generated by the text encoder and the motion embeddings generated by the corresponding part-specific motion encoder. The training maximizes the diagonal elements, which represent positive pairs represented in green color, while minimizing the off-diagonal elements representing negative pairs with text similarity below a certain threshold represented in red color. This ensures strong alignment between text and motion embeddings for the same body part while discouraging incorrect matches. We illustrate the LLM generated part specific outputs for text descriptions alongside their corresponding part-specific top 1 retrieval results, with the human ML3D ID for the retrieved motions, indicated by the hash symbol. These examples show that the LLM-generated part descriptions provide precise part-specific details. The retrieved motions are also semantically coherent with the input text, demonstrating the overall effectiveness of our prompt strategy and part-specific motion retrieval models. The three retrieved part-specific motions are first trimmed to the same motion duration and then composed into a single full-body motion sequence. This is done by selecting the joint information for each body part from the corresponding retrieved motions. The torso joins from the torso-specific retrieval and similarly for the hands and legs. The global orientation and translation are taken from the leg-specific retrieval, considering that the leg motion is most closely associated with changes in global translation and orientation. We prompt the LLM to provide position information in addition to movement descriptions, as the position of each body part is crucial for spatial motion composition. For example, with the text "a person is swimming," when prompted for position, the leg's description includes parallel to the ground. This detail played a vital role in retrieving the relevant motion sample, which when composed resulted in a semantically coherent motion sequence. All part-specific retrieval models are trained using full-body motion sequences, as the LLM-generated part-specific descriptions often include contextual information about other body parts. By utilizing full-body motion sequences, we leverage intra-joint relationships, leading to more coherent and semantically accurate motion retrieval. However, we limit our approach to three parts: torso, hands, and legs, and avoid treating left and right as separate retrievals. For instance, in the text "a person is taking large strides while walking," separately retrieved motion for the left and right legs can become asynchronous when composed into a single motion sequence. Let's look at some examples to understand the effectiveness of the MoRAG approach in generalizing across the language space. We compared our results with the TMR approach and observed that MoRAG with LLM-generated description resolved several issues that previously caused failures. For instance, in the cases of rephrasing, spelling errors, and word substitutions, the LLM-generated descriptions for the original and transformed text are largely similar. This ensures that MoRAG retrieves consistent results, avoiding failures that occur with approaches like TMR. These examples demonstrate the robustness of MoRAG in handling linguistic variations effectively. We conducted a qualitative analysis comparing the MoRAG approach with TMR++, the state-of-the-art motion retrieval method, across three key aspects: generalizability, zero-shot capability, and diversity. MoRAG leverages part-specific details, providing greater flexibility to capture subtle variations in text descriptions. This enables finer detail representation and more precise motion retrieval, even for complex or unseen text inputs. For example, consider the text input "a person is eating" while standing. Existing models can retrieve relevant samples directly, as such actions are explicitly present in the dataset. However, for variations like "a person is eating while seated on the ground," existing models struggle due to the lack of relevant samples. In this case, they retrieve the closest possible matches, such as "a person is sitting on the ground." In contrast, MoRAG retrieves individual sitting and eating samples, which are easier to find due to their relevance in the dataset. By composing these samples, MoRAG constructs semantically coherent and contextually appropriate motions. Our approach facilitates the construction of motion sequences for unseen text phrases, also known as zero-shot. While the input text may be novel, the LLM-generated part-specific descriptions are not entirely unknown. Relevant samples where the desired action is performed by specific body parts already exist. Our method retrieves such samples independently for each body part and integrates them to construct coherent motion sequences. As we can see here, we compare zero-shot capability of MoRAG approach with TMR++ for diverse text sequences. In each of the text sequence, MoRAG outperforms TMR++. MoRAG constructs a diverse set of motion samples for a given input text by using two main factors. First, the LLM's ability to generate diverse text descriptions for the same prompt, and second, different combinations of the retrieved part-specific motion samples. This approach allows MoRAG to create a wide variety of motion sequences that are both semantically coherent and diverse. As we can observe here, we provide diverse motion sequences for a single text input. Now MoRAG diffuse. MoRAG constructed motion samples are used to condition the training of the Remo diffuse model, a state-of-the-art motion diffusion model. We refer to this approach as MoRAG diffuse. Our observations show that conditioning the diffusion model with enhanced retrieved motion samples improves the performance of the generated samples. We provide both qualitative and quantitative analysis comparing the MoRAG diffuse with the baseline model Remo diffuse. Similar to MoRAG, we evaluate MoRAG diffuse model on three fronts. The MoRAG diffuse model shows a strong comprehension of the language space, allowing it to effectively capture variations in text descriptions and generate more accurate motion sequences. For example, while Remo diffuse can generate a motion for a simple text description like lunging, it struggles to adapt to more subtle variations in the text. In contrast, MoRAG diffuse effectively captures these fine-grained details, generating more nuanced and accurate motion sequences. Remo diffuse struggles to generate motion sequences for unseen text descriptions. However, with the effective conditioning of MoRAG generated samples, MoRAG diffuse is able to generate coherent and semantically accurate motion sequences, even for novel text inputs. As we can see here, MoRAG diffuse is able to generate motion sequences for unseen text descriptions. The diverse samples produced by MoRAG enhance the diversity of MoRAG diffuse, allowing it to generate a wider range of motion sequences that are both semantically coherent and varied. As you can observe here, MoRAG diffuse generate diverse motion sequences for a given text input. We compare the results of text-to-motion generation between our method and state-of-the-art diffusion-based methods on the human ML3D test set. Our method outperforms others in terms of semantic relevance, diversity, and multimodality. In the results, green indicates the best performance, while purple indicates the second best results. The key to high-quality and generalizable text condition motion generation model lies in improving the alignment between text and motion representations. Through our MoRAG framework, we show that by leveraging part-specific retrieval and large language models, we can enhance the generation of semantically coherent and diverse motion sequences, significantly improving both the quality and generalization of the model. Thank you.